So consider the long exact sequence corresponding to this pair xp minus 1 which lies within xp. So the sequence keeps coming in like this. So hn plus 1 xp, then hn plus 1 xp comma xp minus 1, then reduce index, go to hn xp minus 1, hn xp, hn xp xp minus 1, here, here, and so on. So this will keep on going. So we have long exact sequence for this pair. Now we consider long exact sequence for another pair. So the second pair we consider is xp is contained within xp plus 1. So again we will have a long exact sequence corresponding to this pair in homology. So this goes from hn plus 1 xp plus 1, take the relative pair, then go to xp xp plus 1, take the relative pair xp xp plus 1. So this is a staircase diagram. Notice the each corner. Here you have xp plus 1, you have hn plus 1. Here again the space is the same, the bigger space xp plus 1, but your index has decreased by 1. Again this bigger space is the same and your index has decreased by 1. So notice the corners of the staircase. So these are important because it is according to the corners that we fit the staircase with each other. So now we will consider another pair, and obviously the next pair is going to be xp plus 1 is contained within xp plus 2. So now our pair is xp plus 1 is contained within xp plus 2. So again you have a long exact sequence in homology. You start with the bigger space xp plus 2 hn plus 1. Again the sequence is coming in from here. Take the relative pair, then you go to xp plus 1 xp plus 2, again the relative pair p plus 1 p plus 2, and then this will keep going so on. So again notice the corners. It is the corners where we will fit the sequences next to each other. So at every corner you have the bigger space. You start with xp plus 2 here, you have xp plus 2 here, but the index is decreased. You have n plus 1 here, you have n here. Next corner again the bigger space which is xp plus 2, and the index has decreased by 1. You have n minus 1, and so on. So let us now put all three long exact sequences together. Now we fit all three of the long exact sequences together on a single sheet. So if you do that, you will get such a diagram. So notice the corners, how the corners are fitting. So the fitting of the corners is giving you this arrows in the vertical diagram. So again you have these arrows in the this vertical column here. So obviously there is an arrow coming in, there is an arrow going out, arrow coming in, arrow going out. And if we extend the long exact sequence on the left side, you will also have arrows coming in like this. Precisely the way the arrows are coming in here, the arrows would be coming in here like this. So you can find this exact diagram on page 3 of spectral sequences. This is online notes of Hatcher. So now you can think of these columns actually being induced by filtration. So you have some filtration like this, xp minus 1 going on to xp, which goes on to xp plus 1, and so on. Now you apply the functor hn minus 1 to it, you land up here in this column. You apply a functor hn to it, you land in this column. You apply a functor hn plus 1 to it, you land in this column. So ultimately we will set this diagram in a bigraded complex because this will give us the start of our spectral sequence. So to do that we have to have bigrading. So instead of n you write it as p plus q. So p and q will give you the bigrading, where to put this in particular row or column of our page. So then we set E as this direct sum over all p and q for columns. So this entire thing you take direct sum of all these things included in it, you include this also. So all these columns and these columns, they form E. So this entire thing is E. This is also E because there is bigrading. So you have grading in P as well as grading in Q. And A is the direct sum of these spaces here, here, and here. This is just A. So this is A, direct sum of all these things. And this is also A. You have direct sum of all these things. So this is also A. So you're going from A to E, then again to A, This is again a part of A. Then you're going to E, then again you're going to A, and so on. So you have this A, E, A, E, A. But notice that within A there is a map. So every time you are sitting in A, you're also looking at this map which is within A. Here when you're sitting at E, there is no map connecting this with this, this with this. So in E, within E there is no map, but there is a map within A. So there is a map going from A to A, and say that map is alpha, which is induced by alpha. So for every long exact sequence you put in some alpha, it will give you the corresponding map. So obviously the maps are also bigraded. So there is a map going from A to A, and you call this map as alpha. And obviously A to E are connected, and the way they are connected, you have to think about individual long exact sequences connecting. So this arrow is coming from this arrow, and then it is going into here. So this arrow induces this arrow. Alpha is induced by just this map and this arrow. So let us give names to these arrows. So A going into E, you call it beta. So all these maps put together will induce beta. So we will also write beta here. This is not correct notation, but just to make it clear that all these maps are generating beta. And similarly here, from E to A, say you have gamma. So all these maps are generating gamma. So put gamma here. And the vertical column maps are alpha. So again, you ultimately set it in a bigraded complex. You write n is equal to p plus q, and set E as direct sum like this. So instead of n, you're writing p plus q, and A as like this. Just the homology groups, not the relative pair. So there are no relative pairs here. There are relative pairs in E. So this is important. You see there are relative pairs in E. There are no relative pairs in A. Now this will give you this triangle like this, and this triangle is called exact couple. You have two things. You have A and E as the modules. So A goes to A goes to E goes to A, and then you have alpha, beta, and gamma, precisely like this. So A goes to A, this is alpha right here. This is after you apply alpha, you apply beta to land in E. So you have beta to land in E. Again, then you apply gamma to land in A, gamma to A. Then again, you have to apply alpha, because the way we are working is via long exact sequence. You just pick one long exact sequence. First you apply this map, then this map, then you have to work with this map, then this map. So after alpha, again you have beta, gamma, then here again you have alpha. So standard is you first apply alpha, then beta, then gamma, then alpha. So alpha, beta, gamma, alpha. So again you're starting with beta, gamma, alpha, then again you look at the long exact sequence, beta, gamma, alpha. So beta, gamma, alpha, beta, gamma, alpha. So that's how you get this exact couple. Now there are few things you need to notice properly is that alpha has bi-degree 1 minus 1, beta has bi-degree 0 0, and gamma has bi-degree minus 1 0. So let us see what this means. So let us first focus on this. Alpha has bi-degree 1 minus 1. So notice that this alpha is a map within the columns. So first focus here. So you have this index as p minus 1. So this hn you should write as p minus 1 is the first index, and then q plus 1 has to be second index, because the sum is n. You sum this with this, you get p plus q, and we are setting p plus q as n. So and this index, the first index, has to match with this index here. So you're going from p minus 1, q plus 1, you're going here. Here you have just n, and first index is p. So this you can rewrite again as hp. It matches your xp here. You can write p plus q or p comma q, which means that it is p plus q. So again this p plus q is n, so you don't have to worry. So you're going from p minus 1 to p, so therefore you're adding 1. You're going from q plus 1 to q, so you are subtracting 1. That is why alpha has bi-degree 1 minus 1. You can correspondingly see it in this column also. This you write as alpha. So here again you will write first index has to be p. It matches the space p. So if first index is p and your index is n plus 1, then it has to be the case, then the second index has to be q plus 1. That's how you will get p plus q plus 1, and p plus q is n. So you get n plus 1. So space is xp. For this you can again you see the space is p plus 1. So now you're writing h p plus 1 but your total index is n plus 1. So you just have to have q here. So then you have p plus q plus 1. P plus q is n, and then this plus 1 gives you plus 1 here, and your space is xp plus 1. So notice that the first index has to match the index of your space. This p plus 1 has to match this index. So again, we are going from p to p plus 1. So you're adding 1, and you're going from q plus 1 to q. So you're subtracting 1. So alpha has by degree 1 minus 1. So let us now see beta. So beta does not do anything. Beta has by degree 0, 0. So notice that the map beta is right here. So what does it do? Your index has to match the index here. So you have p here, n plus 1 here, p here, n plus 1 here. So the index has not changed. In fact, just like you write it like this, you can write this hn plus 1 again as xp comma q plus 1, because your index has to add to n plus 1, and you have xp comma xp minus 1. So again, the bigger space index p has to match this p here. So nothing has been changed. Similarly here, if you go from here to here, again you have this bigger space as xp, and you have hn here. Again you have hn here, xp here. Again, if you have to write it, you have to write as h of p comma q. So nothing has changed. So from pq you go to pq here. From p comma q plus 1 you go to p comma q plus 1 here. So beta has by degree 0, 0. Now we talk about gamma. So gamma has by degree minus 1, 0. So again, focus on this. So this we rewrote like this: p minus 1 q plus 1. And here this is same as this, which is p comma q plus 1. So from p you're going to p minus 1. Q plus 1 is remaining the same. So you have minus 1, 0. So another case, let us see here. Again you have gamma here. Now here this is n. We have said this p comma q, obviously, because p plus q is n. Now this is coming from n plus 1, and this n plus 1 comes from p plus 1 comma q, precisely because your first space is p plus 1. So you have p plus 1, and then you add p plus 1 plus q will give you n plus 1. Because q is always complementary degree. To calculate q, you always set q is equal to n minus p. So this is just your complementary degree. So now you're going from p plus 1 comma q to pq. Again, q is remaining the same. You're going from p plus 1 to p, so you're decreasing this by 1. So that's why you have minus 1, 0. Now we say that this couple is exact. So this couple is exact because the long exact sequences are exact. So this is built out of long exact sequences. So these are exact. So now let us just go through this diagram and see why this is so. So again, you have alpha, beta, gamma, and so on. So focus on first alpha. So kernel of alpha is equal to image of gamma because of the long exact sequence. So kernel of alpha is equal to image of gamma. You already know that. Now you're saying kernel of beta is equal to image of alpha. Again, this beta is sitting ahead of alpha. So kernel of beta is equal to image of alpha because of the staircase diagram. We have long exact sequences. Finally, again, you have kernel of gamma is equal to image of beta, again because of our long exact sequence. So you get an exact couple. So from this exact couple, so this exact couple contains 5 things. It is a 5 tuple. So from this exact couple, we can build a spectral sequence. So we copy everything to the filtration. Now in this, I have done nothing. I have just replaced xp with filtration of our space fp. So instead of topological spaces, now you can use filtration. Only thing is here you have to modulo out the previous filtration. So from fp you have to modulo out fp minus 1. So these are the corresponding relative pairs. So now you can use it for modules, for rings, and so on if you have a filtration given to you. So again, you have a bigraded complex. So complex E comes from bigrading all these things. This gives you E. This will give you A. Again, you have direct sum here, but you also have these map alpha which are within A. So therefore you have a map from A to A, and then you again go to E, which is direct sum of these two. So from A to E you have beta. From here to here you have map gamma, and then you have alpha. So that's how it is going from A to A. First you apply alpha, then beta, and then gamma, and so on. So you keep going like this. So again you have this map A here, and then you have alpha going to E, which is beta. So this is how you get this exact triangle. Everything carries over from our previous discussion alpha has pi degree 1 minus 1, beta has pi degree 0 0, and gamma has pi degree minus 1 0. Again, because you have long exact sequence in this, alpha, beta, gamma come from the long exact sequence. You have kernel of alpha is equal to image of gamma, kernel of beta is equal to image of alpha, kernel of gamma is equal to image of beta. So every filtration leads you to exact couple. So our story is like this. You start with the filtration. Once you have a filtration, you start building long exact sequence of pairs. Once you have the long exact sequence of pairs, you fit them in a staircase diagram. So once you have in a staircase diagram, then you have just two things, E and A, two modules alternating, E, A, E, A. So you have two modules, you will get E and A. But you can distinguish them because A will have a map within itself, which is alpha. So A will have a map within itself, which is alpha, and E is connected to A via long exact sequence. And so the other two things in the long exact sequence, the map going from E to A, so map going from E to A and map coming into E, these are the other two things. So there are two other things, which is beta and gamma. So you have filtration, from there you get a long exact sequence of pairs, from there you get a staircase, then you get these two things, E and A, and you have these maps alpha, beta, and gamma coming from your long exact sequence of pairs. So they will have pi degree like this, and you get an exact couple. So from here you get exact couple. So what have we done? We have started with the filtration, and we have ended up at an exact couple. And from this exact couple, we can easily build a spectral sequence. So our next step is to go from this exact couple to spectral sequence. So that will lead from filtration, you can go directly to a spectral sequence.